speaker today. We are very pleased to have Professor Acharya from Jadavpur University, Department of Mechanical Engineering. His specialty is in fracture mechanics with research focus in fatigue, fracture, and deformation of metals at low and high temperatures. He's been involved in many sponsored projects through strategic areas through BARC, IGCAR, BRNS, and so on, and as well as DRDO. He's guided 11 PhD and 20 master's theses, and he has more than 70 journal publications and 80 international conference proceedings. Interestingly, he's been exploring the concept of a quantity called critical fracture energy as a material property for measuring the fracture energy and serving as a fracture criterion for short cracks at low temperatures. So today's lecture will focus on some of these aspects, and we're very pleased to have him speak to us. Professor Acharya, please go ahead.
So good evening, everybody. First of all, I must express my gratitude to InSIS for giving me the platform to share the idea of critical fracture energy Gfr-A new fracture parameters, on which we worked in last 20 years. And then also all the viewers and are present here. So first I must say that I am presenting on behalf of a team who are working in this particular topic or area in last 20 years. Let me introduce Professor Shankar, Mechanical Engineering, Jadavpur University, who is also my teacher as well as colleague. Dr. Jayantu Chattopadhyay from BARC is currently head Reactor Safety Division. Professor Parthopratim De from IIST Shivpur, and Dr. Sukalpo Chaudhary from Jadavpur University. Myself, Professor Shankar and Dr. Jayantu Chattopadhyay actually explored the idea initially. And then Dr. Parthopratim De and Sukalpo Chaudhary did their PhD on this area. So what I am presenting today is on behalf of the team. So today the topic is critical fracture energy Gfr, a new fracture parameter for ductile crack growth. It is new as because it is not accepted in any standard, or it is not also well known within the community. Initially, it was actually pioneered by two people, Stephen Marie and Stephen Chapouliat in France. And then we also received some requests from Dr. Khuswa of BARC to explore the idea in our country on PHWR pipes, which BARC are using. And then we started our research. This is the beginning of our research. We know that for ductile material, the deformation phenomena, having a crack or any discontinuity within the member, requires to model the stable crack growth, because before failure, a huge amount of stable crack growth occurs. So while modeling or simulating the deformation behavior of ductile material, either in specimen level or in component level, what we are facing that if we look in this diagram, we have simulated the load versus LLD curve or load line displacement curve. If we give only elastoplastic material property as input without any crack growth data, then the simulated curve will take the shape of this red color. But the actual experimental curve is represented by this black. There is a load drop while crack growth takes place. But if we don't give any input of crack growth phenomena to simulate, then this load drop will not be captured in simulation. So stationary load versus LLD curve from stationary crack will go upward the actual experimental curve. And if we give some crack growth data as material input, then we can simulate. Here look in the right side curve, simulated curve is more or less at par with the experimental curve, as because in the right side we have given some crack growth information, crack growth data, either in terms of GR curve or in terms of CTOD versus displacement or some micromechanical model like Garson model. So here what I can conclude, to simulate the real phenomena in ductile material, we must have to give some crack growth data as input along with the elastoplastic material property. Here remains the importance of a crack growth parameter. So crack growth parameter is an input, important material input for simulation of load deformation in case of ductile material. And the existing crack growth parameters which are popularly used, mostly used parameter are J delta A curve, you know JR curve. But the limitation in JR curve is that the characteristics or the JR curve data is not only a material specific value, but also it depends on the constraint level, geometry of the component, nature of the crack, nature of the loading. It will vary from CT to TPB specimen, from tension to bending load, and even on the depending on the crack geometry, crack size, A by W ratio. So partly resolved, this problem in the JR curve is partly resolved introducing a second parameter like Q stress or T stress. But still, even using the two parameter theory, it cannot account for the in plane or out of plane constraints equally. If we discuss about the micromechanical models or local phenomena model, local approach like Garson, etc., they are also, it depends on the mesh size, geometry, and the most difficulty to identify the material parameter, the Garson parameters. And the dependence of Garson parameters on other constraint level is still also difficult. So what is the current situation? That JR curve is popular, widely used, partly resolved with the two parameter theory, but not completely resolved. So from here in fracture mechanics community, it was always desired, I can say desired, that if a representative fracture parameter is available, which can be a material property, that can resolve the issue and will be of immense advantage in application. So because of this, so many people are working with the fracture parameter. And then an alternative approach came from the French people, Stephen Chapelier and Stephen Marie. If we review the crack growth process, that crack growth phenomena influenced by plasticity at the crack tip in case of ductile material. It depends on the plasticity, size of the plasticity or plastic zone size, energy dissipated for this plasticity, etc. And whenever input energy is supplied to the crack system, it includes two parts. One, to ensure the fracture process itself, which is locally arrested, and another also to supply the global plastic dissipative energy, which depends on the size of the plasticity around the crack tip. Additional energy in the fracture process also goes for creating new surfaces. And if we try to observe the rate of energy dissipation, and if we term it as R, if it is only the dissipative energy rate, here rate means with respect to area, we can calculate it subtracting the elastic energy from the U total and get the total energy dissipative rate. And it is decomposed in two parts, what I have told earlier. One responsible for global plasticity and another for fracture process. Turner initially actually worked on this particular area, and he gave this idea to decompose in two parts. And based on this idea, a new fracture parameter Gfr was introduced by Marie and Chapelier. And also they claimed on their based on their investigation that this Gfr can be treated as a material property. What I am emphasizing on material property, they observed that it is independent of the constraint level. So if we look the Turner proposition that this curve shows the total dissipative energy rate in terms of crack length decreases with the increment in the crack length and ultimately saturates. This was the observation by Turner. And if we decompose it, then two parts are there in this rate. One to supply the global plasticity level, another to supply the fracture process. And it was also Mary and Chapoulier did some experiment on two different specimen level, and they also found the same observation like Turner's proposition, that the total dissipative energy rate ultimately decreasing with the crack length and saturates. First observation. And secondly, they also calculated the reference stress for each specimen of the same material. And they also observed that the value of reference stress did not change after a certain crack length. So if we conclude on these two observations, that the rate of dissipative energy saturated ultimately and the reference stress remains constant, we can say the reference stress is the reflection of the global plasticity level. So if reference stress remains constant after certain crack growth, then it can be concluded or rather interpreted that at larger crack growth, the rate of change to supply global plasticity is 0. There is no change, so rate of change is 0. So if this part becomes 0, the ductile dA becomes 0 at higher crack length. So only the residual part remains the energy responsible for fracture process. So ultimately at larger crack growth, the rate is coming or contributed only by the energy required at the fracture process. From this observation, they tried to interpret that whether this part of energy can be used to simulate the ductile crack growth, as because it can be estimated at larger crack growth and it can be explored whether this value remains constant or material representative or not. So from this idea, they were encouraged to estimate the value of this fracture energy, which they named as critical fracture energy. If we look, our interest is to estimate this fracture energy, then we have to go again in the load deflection curve. We know that if here LLD is only the plastic part of the displacement, if we consider, then area under the curve is the estimate of the value for calculating J value, J integral value multiplied with the eta factor and etc. So at larger crack, energy required at the crack tip is related to fracture process zone and a measure of critical fracture energy. This was the first observation by Mary and Chapoulier. Look here, two stationary crack which are obtained by simulation are there, and one is the experimental curve. And whenever deformation occurs with crack growth, the first curve is of crack length A and the second curve is of crack length A plus dA. So when starting at the crack length A, load goes up to A without any crack growth. And then after reaching the point A, if there is no crack growth phenomena, then we can increase the displacement without any crack growth and can arrive at the point D, which is a point on a stationary crack. But if here crack growth occurs, as it is observed in the experimental curve, that here crack growth occurs, and to arrive at the displacement 2, delta 2, we ultimately arrived at a point C at some lower load compared to D. So here the energy between the or within the area entangled by ABCD is the difference between the J at point D and J at point A. whether this multiplied with the area B into dA gives the area, as because J is per unit area. So this total energy is represented in this main phenomena. Gc into B into dA is equal to the area entangled by the quadrilateral ABCD, where Gc is equivalent to some energy release rate, like Griffith's energy release rate in ADFM. Now, Gc can be calculated if we can calculate this area. To calculate this area, we require two simulated curve of crack length A and A plus dA, which are of course stationary crack, and the experimental curve. If we obtain this, then we can evaluate the area under the ABCD, and that can be equated to Gc into B into D, from which Gc can be calculated. And now this Gc is proportional to the crack extension. To normalize the crack extension length, Gc is again defined in terms of this. Gc is equal to Gfr into dA, where Gfr is independent of the extension of crack. In this way, a definition of Gfr, which is actually named critical fracture energy and noted by Gfr, comes from Chapulia and Mary's work. And also, this Gfr also can be derived directly from J integral. If we look this derivation, here the DGPL is given in terms of DGPL del A and DGPL d delta, one with respect to crack length, another with respect to displacement on cracked part. And ultimately, it will give us the definition of earnest J integral like this. If this earnest J integral is equated to Gc, then from definition of Gfr, Gfr is nothing but dGmpl by dA. So if we can estimate the Jmpl, here Mpl means M stands for the earnest integral and PL stands for the only taking the plastic part of the deformation. So if we can estimate the slope of the curve Jmpl versus dA, that slope also can represent or can be an estimate of the value of Gf. So first two different methods. The first method in the earlier slide which I have shown, where the value of Gfr is calculated from the area ABCD, that's named as graphical method. And this method is known as JMPL or DGMPL DA method. So the contribution of Mary and Chapulia is that they found out, or that they proposed two concrete methods from which the value of this critical fracture energy can be evaluated. Because if we like to check whether this is a material property, whether it depends on the constant or not, first of all, we have to know the mechanism to evaluate it. So Mary and Chapulia proposed these two different methods for evaluating Gfr for a material based on some simulated or load versus LLD curve for stationary crack and one experimental curve. This is the method for estimation of critical fracture energy. From here, we can evaluate Gfr from the graphical method. And from the slope of this, if the slope is fitted with a straight line, then you look the gradient of the curve actually representing the value of Gfr. So to calculate Gfr, either we have to go by graphical method or we have to follow the JMPL versus delta A curve. This was the starting point for us. When we received some documents or papers from Dr. Kushwaha, we got this idea from the works of Mary and Chapulia. And we were requested to explore the idea on some material which BRC is using. So we formulated a project on BRNS and we started our investigation. The material was SA333 group 6 carbon steel, and it is used in the PHWR pipes and other components for BARC there at their nuclear plants. The composition is given and also the tensile property. mechanical property for this particular material we received from Park. And what we initially started, we started with a CT specimen and pipes under 4-point bending. Here the loading type is bending, and for CT compact tensile specimen. And we received this data. You look in the left side, the experimental data for the CT specimen for fracture toughness test is given. This is the load versus LLD curve from fracture toughness. Unloading part are there to calculate the crack length. And this is the JMPL versus delta A curve. So these two material data we received for pipes and CT specimen. So what we did, following already the methods are there proposed by Chapulier, we estimated the GFR for different crack length. Look in the left diagram, simulated curves are of 26 millimeter, 27 millimeter, 28 millimeter. So based on the two simulated curve of 26 millimeter and 27 millimeter, we can estimate a value of GFR. Again, between 27 and 28, also we can estimate the value of GFR. Again, between 26 and 28, we can estimate the value of GFR. So we can measure the value of GFR at different initial crack length and for different amount of crack extension by graphical method using only a single experimental data on fracture toughness. But in case of JMPL versus delta A data, only one value of GFR is possible to be estimated from the slope. Using this conception, we estimated, these are the load versus LLD diagram for pipes. We simulated using ADINA and Work3D to finite element software and estimated the value of GFR. Our initial observation was that GFR for CT specimen are observed to be higher than the values of GFR for pipes under 4-point bending. This was initial observation on behalf of us. And again, we recalculate, but the same thing occurred for several times, giving us some implication that the estimation procedure either may require some correction or the conception may not be valid for this material. So we started to reinvestigate the process and try to understand why is there any chance or is there any reason that if we estimate the value of GFR by this process, it should be lower in case of pipes under bending? On our reinvestigation, what we look, we got the idea from the Johur's paper that in a cracked component, when displacement occurs, in the total displacement is contributed by two pockets. One, non-crack component of the displacement. Suppose on the same component, if there is no crack at all, and if we apply load, depending on the compliance of the specimen, there will be a displacement, which is where there is no contribution of presence of crack in the displacement. That is non-crack component of the non-crack part of the displacement. And if we introduce a crack on the same component, naturally on the same load, the amount of displacement will be increased. So this additional displacement is contributed from the crack, presence of the crack, which is called cracked component of the displacement. Now, what happens in CT and pipe? If we calculate the compliance or rather stiffness, we look that the non-crack component of the displacement in case of pipe is larger, much higher than the non-crack component of the displacement in case of compact tensile specimen, CT specimen. But while estimating the GFR or energy balance, we did not contribute or did not consider the effect of non-crack part of the displacement. So again, we reevaluate the procedure. And here you look, the left curve stands for the total displacement. Total displacement load versus total displacement contributed by non-crack part and crack part. As this is the non-crack component of the displacement for the same specimen or the component. And if we subtract this part of displacement from the total, then we get the crack displacement versus load versus crack displacement. You may ask, what is the significance in estimating the GFR? Look, here we are saying that how the point D is obtained or point B is obtained. From the point A, we are drawing a constant displacement line to obtain the B. And from C, we are drawing constant displacement line on the curve A to get the point D. But if we consider the same points, the presence of ABCD on crack displacement versus load line, as total displacement remain constant between A and B, and as there is a non-crack part of the displacement, so the actual crack displacement when we are putting the line AB, it is decreasing. So line AB will be like this, and actual constant crack displacement line should be AB dash. So if we like to draw constant crack displacement line on the load line displacement, then the line should be like this. And we have to consider the energy entangled within this trapezoid, which are the energy due to non-crack part of the displacement. And considering all these things, the formula to calculate GFR is partly modified for graphical method. How? Initially, we got GFR into B into dA square was only the area of the quadrilateral, but now these two area, which depends on the non-crack compliance of the component, will be included. Look now, for pipe, this area will come higher, but for CT, this area contributed from the non-crack compliance is very less. According to Chapuliat and Mary's method, we were estimating the value of GFR based on only the area ABCD. This part was missing. And if this part is higher on bending load, what should happen? The value should come less compared to actual, which actually happened in case of pipes under 4-point bending. So from this idea, we also again derived the JMPL based on this crack and non-crack part, and ultimately look, a modified Ernst integral, J integral, we got this expression. You look in the right hand side term, on the second term is the coming from the non-crack part or compliance of the component, which will vary depending on the whether it is a CT specimen or pipe, whether the load is tension or bending, and if it is included within our calculation of JMPL dash, then GFR will be properly calculated. This first, if we say this was the first contribution in the area of GFR from our side. We also communicated this idea with Chapuliat and Murray. They also confirmed the idea. And based on this idea, what we did, we applied the process where consideration of the non-crack compliance is there while evaluating GFR is applied. We applied on CT specimen, TPB specimen, 3-point bend specimen, CT specimen with different thickness, different initial crack length, and for TPB also we varied the thickness, and in component level, pipes under 4-point bending and elbow, you look elbow. So we received the experimental data, pipes under 4-point bending with circumferential through wall crack, but for elbow there were variation in opening bending moment and closing bending moment, because depending on the load applied as this fixture, if you know if the load is tensile load, then it is a opening bending moment. But if it is a compressive load, then it will be a closing bending moment. So variation in geometry, variation in size, variation in initial crack length, variation in loading type, tension, bending, closing bending moment, opening bending moment. So we try to vary as far as possible. And the material data obtained in the courtesy of NML, Jamshedpur and ACRC, both we received through PRC. And this was the finite element simulation for elbow pipe. We did it in ADINA and Warp 3D. And this was the final result. You look, we have calculated GFR for different initial crack angle on pipe for CT specimen, for elbow with closing bending moment, opening bending moment, lot of variations are there. And we estimated the GFR from graphical method. This column represents the value of GFR obtained from graphical method, and this value obtained from JMPL delta A method. Here I have shown a lot of data obtained. And then we try to estimate the standard deviation of the data obtained. So what we obtained, that the mean value came around 250 and with a standard deviation of 23.76. So from these data, we can measure the nature of the scatter and estimate of the scatter. The standard deviation is here estimated to be less than 10% of the mean value, which giving some confidence that there is a possibility of GFR to be used as a material property, even with the variation. Look here, the variation in method. Here we have mixed both the data, either coming from graphical or from JMPL delta A. Geometry varies with CT, TPB, pipe, elbow. Load vary, tension, bending moment, closing, opening, and variation also in initial crack length and also the crack extension. So with all these possible variations, we try to disturb GFR. If it depends on all these parameters, it is anticipated that the scatter will be of some higher value. But here, the standard deviation is restricted within 10% of the mean value. So with this idea, we rather than thought that there is a possibility of GFR to be a material constant. It can be independent of geometry, loading type, and crack length. But why we require these data? Ultimately, we require these data to simulate the load deformation characteristics for growing crack, where crack growth will be there. So how far GFR is capable to simulate experimental curve with growing crack? How far GFR is capable to predict load versus LLD curve and crack length, the crack extension, because it is a crack growth parameter. That is to be tested. If GFR is to be accepted as a material property, then we have to use the same value of GFR, whether it is a pipe, whether it is a CT, TPB, whether the load is 3-point bending or 4-point bending or tension, whatever may be the initial crack length. In all the cases, if we use the same value of GFR and if we can simulate the load versus LLD curve, and if it matches with the experimental curve, then it can be a confidence that GFR can be treated as or used as fracture parameter. So that we did. Before we named this reverse simulation, because we estimated the GFR from this experimental load deformation curve, and now again we are going to simulate the same curve using the value of GFR. So it is named as reverse simulation. So what we require, we know first that the value of J integral, can be obtained if we get the load versus plastic deformation, from this area using eta factor. From this expression, it is a standard practice. We can estimate the value of J integral. So first of all, Suppose we like to simulate the load deformation curve for a CT specimen with known initial crack length, known thickness, etc. So we can model the CT specimen in some finite element software and can generate the load versus LLD curve for stationary crack. And there we don't require to give crack growth data as input. And we have to simulate two simulated curve, one with crack length A0, another with A1, where A1 is equal to A0 plus dA, some del dA amount of additional crack. And these two simulated curves are to be generated using some finite element simulation package. And then we can evaluate the J integral on these stationary crack at every displacement level until the value of J becomes Ji, the J initiation. Here we must say that crack initiation point or the issue of crack initiation is not resolved by Gfr. Once crack initiation is there, then for the stable crack growth part, Gfr can help when and how crack growth will take place. But the initiation requires some material data. Here we have used J initiation. This property was already available to us. So on the stationary crack, we have to evaluate J integral at every incremental displacement. And when the J value will come Ji within a tolerance, then we allow crack growth. We are now ready to happen or occur crack growth. Now crack growth is going to be occurred because J has reached at the value J initiation. So this point is marked on the stationary crack curve. If we go to the next slide, here you look, this point A is on simulated curve for crack length A. And here the value of J becomes Ji. So this is a point where some crack growth will take place. Now, after reaching this point, what we will do, we will select a second point on the second simulated curve or curve with A plus delta A crack length, simulated curve. And based on these 2 points, we will estimate the area of A dash, B dash, C dash, D dash, considering the, because if we get 2 points, we can draw the other points and we get the 4 points. In this way, we can calculate the area under the quadrilateral, even considering the non-crack compliance. And if for this second point, it is observed that the value of Gfr calculated based on the area entangled, look here, this is a first point and this is a second point. C is the point on the stationary crack of A plus delta. So if these 2 points are known, then we can project a vertical line, we can get this point. If we know the non-crack compliance, we can get this point. So all these points are available. From these points, we can calculate the area. Now we can calculate the Gfr. So for every second point on the stationary crack of A plus delta A, the value of Gfr will come. And when the calculated value of Gfr, look, Gfr calculated minus Gfr already we have given as material property. Suppose in our case it is 250. When the difference between the calculated Gfr and the material property Gfr given is below a tolerance value or some very small value epsilon, then C is the point, or C is accepted as the point on the experimental curve having crack length A1. So now C will be a point on the experimental curve. So first point on the experimental curve was obtained as A, where initiation started. Then a second point, C is obtained with crack length A plus delta A. In this way, after reaching C, then again we take some another simulated curve of A plus 2 delta A, and again the search process will be repeated. And in this way, several points on the experimental curve will be obtained using the simulated stationary crack and the value of Gfr as input. This reverse simulation was based on the conception or observation given by Joyce in several experiments, what Joyce observed that the load, displacement and crack length, that is a unique point on the load versus LLD curve. Whether it is stationary or flowing crack curve, this point will be unique. Based on this idea, this reverse simulation was done. And what was the observation? Look, we simulated CT and TPB and pipe and elbow, all this. The matching was very good. The circles or the points are from our prediction and the actual experiment curve is given here. And we did it for not only for CT, but CT, pipe, and this kind of matching with experimental and simulator we received. Number of CT specimen elbow pipes were applied, whether GFR can predict it or not. From the curves, it was encouraging, and we estimated the quantitative values. Because our interest is mainly on the maximum load value, how our simulation can predict maximum load point on the load versus LLD curve. So capability of predicting maximum load, here we listed. These values are received from experiment and these from reverse simulation using GFR as a material property. GFR as a material property, because the value of GFR was used. Whether it is CT, TPB, pipe, elbow, in all the cases, it was taken the single value 250. And we used a tolerance, the epsilon of 25, just equating with the standard deviation. Standard deviation was 23.75 and we took the tolerance value. If GFR comes within 250 minus plus 25, we converge. Our reverse simulation converges. And also from this, we also predicted the load versus crack length. Load versus crack length. They are also naturally expected good matching, and that we also opted. So, first of all, whether GFR can be used as a fracture parameter, this point was attempted, and then transferability of the fracture parameter obtained in the specimen level to component level, how far it is applicable, these two issues were attempted and we got these observations, because we evaluated GFR from CT or TPB, and that value equally can be transferred or can be applied if it is elbow, if it is pipe, whether it is closing bending moment or opening bending moment. This was our first observation, and this works. Actually, we did it through two projects, BRNS project, and we also published two papers on this, one on the non-crack component of the non-crack issue, another on the transferability issue. So both these was peer review, and this was our work from 2008 to 2012 or 14. But the limitation is there. What will be in case of short crack growth? Because already we have discussed that the value of GFR is only acceptable if it is measured at the higher crack growth, higher crack length. But then how the initiation and also when crack length is not so high, how the load versus LLD line will be predicted? That was a problem. Secondly, is there any relevance of GFR with the crack tip stretch or crack tip deformation? How it is related? So with this issue, actually, after this work, Professor Shankar, he investigated on these issues at CEA, the lab in the France, and he worked in collaborating with Marie and Chapulier. And what he did in his work, that critical fracture energy GFR was extracted from a local stretch of the crack tip. From a local stretch of the crack tip, And for calculating this, he used Nook's final stress theory together with a cohesive traction separation model. This cohesive traction separation model was used to simulate the crack growth phenomena where the surfaces are being separated. And Nook's final stress theory was to connect the stretch with the plastic stretch with the energy balance or energy level. So using these two ideas, he did some investigation. So I will not explain in detail because in a short time it is difficult. But if we take the Nook's theory at the crack tip, here the displacement after certain distance from the crack tip for a given crack length, and if we take the difference, one after crack length, crack extension, look here the first U represent the displacement at the crack tip itself after crack extension of amount delta. And this was the before crack extension, it was the displacement at a distance of delta at crack length A. This difference is a constant and delta. This was the Nook's theory or Nook's proposition. This was taken, and from DBCS model, the definition of U or expression of U in terms of U tip we considered, and we also considered the value of J integral in terms of displacement U, sigma y and m. This is a standard expression. If we combine this, then delta can be expressed in terms of like this, dj d sigma 0 and this. And now, if we consider or if we convert or rather interchange the terms, so sigma 0 delta versus capital delta is equated to this. And the right side expression is nothing but the earnest integral or djm per dA. So this can be equated to Gfr. So now Gfr is connected with the plastic stretch, sigma 0 delta PL versus by capital delta. So this was the first rather derivation using Nook's theory and DBCS model. Then some separation law required to simulate the crack growth phenomena. For simulating crack growth, we have used JDA curve, J delta A curve, and at every stage level, we can evaluate the DGMPL DA because we have already got the expression in the previous slide. And now the separation or cohesive zone, using some cohesive zone model, separation will be done. At this point, DGMPL DA will be calculated, and we can estimate the value of GFR. So this was the scheme. And for this scheme, we require some traction separation law. It was Corneck traction separation law was used, and T0 is a material property which is to be derived, which is additional requirement. That T0 was derived from some tensile experiment, the traction tractive force or cohesive strength rather we called, that was derived from some tensile experiment. And using this model, he applied the scheme for two different model. One, this Tu-52B was a French, the material used by the French people, and SA-333 used by Park. And here look, he estimated the value of T0 from experiment. Other values are already available, and he applied the total scheme. What was the observation? He plotted the JMPL and JPL both data versus crack length for the material, these two material. And from this, at every point of crack length, the slope can be estimated, and that slope represents the value of GFR. So this is the plastic stretch data. For estimating the GFR, we require the plastic stretch also at every crack length. And once this obtained, we can evaluate the value of GFR related to plastic stretch, because here GFR is estimated in terms of plastic stretch. And this is the plot of GFR. And look, initially the slope is there, but after a large crack growth, there is a trend of saturation. whether the material is SA333 or 250. So what is the advantage? Now we get the value of GFR at short crack length also, though it is not constant, though it varies with the crack length, and ultimately saturated and being a material constant at a larger crack length, but we can estimate, if we like, what will be the value of GFR at shorter crack length. So one issue is partly resolved, that the value of GFR also can be estimated at a very shorter crack. But still, no correlation with the other material property of the GFR at the shorter crack length is obtained. We have to did this experiment and we have to apply separation law for every particular component or specimen, then we can got this data. So this was resolved by Professor Shankardhar and Stephen and Chappie, Mary Chapulia. This was also published in Pressure Vessel. After this, it was probably 2012 or 11. There a long gap on our work or research on the GFR. In between, we did experiment for master curve on ductile to brittle transition temperature. Material was 20 Mn MO Ni55 steel in collaboration with bar. So for this, we have to do huge amount of fracture toughness tests at various temperature, from high temperature to low temperature, mainly at low temperature. Huge fracture toughness data, CT specimen, TPP specimen, mainly with varied thickness, crack length, etc., etc. After we receive this data, or rather when this data is available to us, then in 2018 we started to think whether this huge amount of available data can be used for exploration of GFR, because this data is already there. So we again started our investigation process on the material 20 Mn MO Ni55 steel, and we planned that our objective will be four. First of all, assessment of the effect of variation in geometry and temperature on critical fracture energy GFR for the material 20 Mn MO Ni55. First of all, at room temperature, whether GFR obtained for different geometry, because different geometry means we have data on CT and TPP. On CT thickness variation is there, on TPP thickness variation are there. So if we evaluate GFR from every possible variation, whether again it can be observed as a material constant or not. Secondly, at every varied temperature data, if we repeat the process, what will be the variation of GFR depending on the temperature? This was the first issue. In the low temperature region, we know the value of ductile stage gradually decreases, and ultimately at some lower temperature the failure phenomena becomes completely brittle. So therefore this range is called ductile to brittle transition range. So crack extension will be reduced as temperature is lowering. So again a question of short crack length. If we have to predict the value of GFR at some lower temperature, again it is related to issue of shorter crack length. And thirdly, the available expression for short crack length to predict GFR, how it depends on the temperature, whether it can be transferred to at low temperature or not. And lastly, we also explored the idea, though not fully completed, that how the value of GFR can be used to model ductile cyclic tearing. Ductile cyclic tearing using the fracture toughness data. Using the fracture toughness. So this was rather this was the thesis plan for Dr. Sukalpo Chowdhury. I have already mentioned. He did his PhD on this area. So what we did experiment for tensile experiment at different low temperature. We did experiment up to minus 140, but here I am going to present only data up to minus 60 because our observation is at minus 80 degrees centigrade, the failure was completely brittle in nature. And as we are talking about the ductile crack growth, so at minus 60 degrees centigrade, we examined the fracture surface. At least there we got some ductile stretch before brittle initiation. So we considered the data up to minus 60 degrees centigrade. So we did first tensile test at different temperature. We did fracture toughness test. Already data was available. And we estimated Gfr for different crack length. This is the room temperature data for different crack, initial crack. Thickness variation was there. From there, for different crack length, we got the value of Gfr. Having a tendency to get that the Gfr value is more or less constant with some standard variation. We again estimated the value. The initial table was from graphical method. Here we use the JMPL versus delta A curve for different initial crack length. And from the slope of the curve, we got the idea. Look here, 355, 342, 382, 336, 331, 339. These are the values for GFR for 20 mn MO Ni55 at room temperature using graphical method in the previous slide and now from JMPL delta A. So this was with a close proximity. So again, we got confident that material is different. Earlier it was SA333, now 20 mn MO Ni55. Again, if there are variation in thickness or A by W ratio, the value of GFR is coming more or less same with a little amount of scatter, acceptable amount of scatter. Here we varied the temperature. Look, here the JMPL versus delta A curves are shown. Minus 60 degree, minus 40, minus 20. And we estimated the value of GFR. And here a little bit larger variation is obtained from 27 to minus 60. From this GFR value at low temperature data, initial observation was this, that for the material 20 mn MO Ni55 still complete brittle failure is at minus 80. So value of GFR is calculated up to minus 60 and then let it fall in GFR value with decreased temperature is primary observation from the experimental data or our GFR value obtained. And this was also published. Then we tried to again reinvestigate the cohesive zone model, but here the PPR model, here the potential function was selected in a different way for which a lot of material data was required. We have to do experiment on plain tensile specimen, round notch, V notch, and also CT specimen of different constraint level. We have to evaluate the cohesive parameters. These are the cohesive parameters which we estimated from these experiments. And we modeled it. Cohesive zone modeling was to implement or separate or rather implement the ductile crack growth in the material. And this was the prediction from cohesive zone modeling. Very good matching on experiment and simulation was observed. So we are confident that this cohesive zone modeling to predict the crack growth is applicable. can be acceptable. So we used this model, and if load versus simulation data are available, load versus LLD data are available, then we can estimate the GFR from the very beginning to large crack growth. In this process, GFR was estimated from the very beginning for different types of CT specimen first, with different initial crack length. So this is the plot of GFR versus crack growth using the cohesive zone model or stretch model, and estimating based on our JMPL versus this curve and graphical method both. Then what to do? We got a variation of GFR versus delta A. Now we fitted the curve. What was our attempt? Here we define the curve in terms of a constant GFR. This GFR is a constant and material property which is obtained at the larger crack, which already we have talked about. But there is a modified GFR. Modified GFR is expressed in terms of GFR at larger crack growth and the other material. It is this fitting is there, and you look, this GFR dash is valid from very short to large, and at very large crack growth, this part will be vanished, the right hand side part will be vanished, and GFR dash will be equal to GFR. This GFR, right side GFR, only GFR is the material constant. Initially with the fitting, we got a new term R. The variation of GFR with crack length is expressed with this equation, where there is a constant material property GFR and another term R is there. For different GFR versus delta A curve I have earlier shown, we estimated the value of R, and also we estimated so many internal properties and compared whether R can be represented in terms of some material property, known material property. What we observed, if we compare this value R with the critical CTOD value, because critical CTOD can be measured. So critical CTOD R, if are mapped or are compared, they are observed to be very close to each other. So now this R can be replaced by CTOD. So for short crack growth, we require another information, the CTOD data. If we vary the temperature, we have to know the CTOD at that particular temperature. If we vary, or if other variation is there, so for defining the GFR at short crack growth, the constant GFR is to be known, along with CTOD data are to be available for that particular type of component or specimen. They can we describe the GFR versus delta A completely from very short crack length to larger crack. So now this was evident in room temperature. But when there will be difference in ductile stretch as temperature being lowered, whether this is applicable to low temperature also or not. This was our second investigation. So again, we fitted the curve. We estimated these the curves are for different low temperature, and we estimated the value of CTOD and obtained the GFR value. This is the constant GFR value. Look, we know the GFR dash versus delta A for a particular at a particular temperature. If we know the CTOD, then we can calculate the GFR at that temperature, and that GFR should be a constant. So when we estimated the constant GFR value from this expression using CTOD data and GFR dash data, what we got a very close data on GFR. The variation was there in case of, look, if we compare this, here this is the value of GFR obtained directly without this fitting, and this is the value of GFR obtained this fitting. Here it comes very close to each other. Here there was variation. This variation because of the variation in ductile stretch. But if we can estimate or include the CTOD information into the expression, then this particular GFR can be treated as a constant. But for lower crack growth or shorter crack length, if we have to predict, then we require this data. At larger crack, it will be irrelevant. This part will be gradually vanishing at higher crack length because of this nature. But at shorter crack length, this part is to be deducted from the constant value. This is the lowering in GFR value. And how much it will be lowered, that is given by this. So in this way, the complete description of the GFR over the shorter crack length, higher crack length. For shorter crack length, some additional data will be required, but it can be defined. And that additional data is nothing but CTOD data. And the same expression can also be applicable even the temperature is lower, where the value of ductile stage is gradually decreasing. So this was our observation. This is the results for CT specimen at different temperature. And again, we use the GFR value for reverse simulation. And we got good matching. We estimated the error for predicting because this reverse simulation is now using the shorter crack length definition of GFR and constant value of GFR at larger crack length. Now, instead of a single value of GFR, we are using this definition of GFR, where at a shorter crack length, or rather we have to supply the CTOD data. Based on this, we reverse simulated and predicted the load versus LLD curve for different specimen at different temperature. These are at different low temperature, up to -60. Because in our idea, the validity of GFR only up to -60. Beyond that, there will be more or less complete brittle failure. So I can finish here also, because the next part.
I think we should leave some time for questions, Professor Acharya.
Yes. I will take only 1 minute. This part is not peer reviewed, this experiment for ductile cyclic tearing. So I am not going to present it, but we have done. Only the thing that we have done here, we have executed the fracture toughness testing with a different extent of unloading. And from this unloading part will be a representative parameter of R ratio, because depending on the Pmax and Pmin, this R ratio can be varied. And depending on this R ratio, we estimated again the J value and tried to compute GFR. Here we have considered also the crack growth due to fatigue also, because total amount of crack growth we decomposed contributed by fatigue and fracture, and from there only fracture part is taken, and then based on the fracture crack extension and J obtained at different R ratio, how GFR comes. This was our part of investigation. There also we successfully, rather our investigation has been successfully observed that the nature of GFR is more or less constant, but I am not going to detail. So up to this, now I am finishing and waiting for your comments or explanation.
Thank you, Professor Acharya. A very interesting talk. Let me just tell the audience, if if you have any questions, please type them in the chat box, and then I'll take them up. I had one. You started by saying that the idea of GFR was to sort of decouple the global plasticity from the fracture process.
Yes, yes.
Am I right? Yeah. So in this sense, why would GFR depend on the initial crack size? I mean, for why does it change for very short cracks?
Because I also shown that Turner proposition was that at lower crack length, the reference stress changes. And global
Yeah, that
plasticity.
was my other question. Your reference stress is how is that defined? Is it just the load divided by the net section area or what?
It is based on this that yes, load divided by the section area.
Section, okay.
So saturation comes after certain crack length.
Okay. The other question I had was you're getting GFR from the slope of the
JMPL versus delta A curve.
delta A. What is the significance of the intercept there? Does that have any meaning?
No, sir, we have not explored the idea of the significance of the intercept. We
The
took
intercept,
only
okay.
the slope. We took only the slope.
Thank you. Okay, so once again, let me ask the audience, if you have any questions, please type them in the chat box. So in a sense, you're using this to well, one object is clear that if you have a component, whether it's a pipe or a bent pipe or so on, subject to a load, what is the maximum load limit that you can tolerate before there's some catastrophic failure? Is that right?
Yeah. This is the major significance that using a single data, we can predict the maximum load with certain accuracy.
Certain accuracy. Okay. And in terms of constraint levels, you mentioned that you had used different constraint levels and checked the reproducibility of GFR as a quantity which is independent of constraint. Is that right?
Yeah, because we varied the component, because when we go from CT to TPB, already
Okay.
some change in constant. If we change the initial crack length, A by W ratio, it also introduces different constant level. If we go for pipe under 4-point bending instead of 3-point bending, again some changes. So using the varied component, loading type, size of initial crack, nature of crack, we tried to vary the constant as input. And then we estimated the GFR value from different components. And their observation that it appears to be more or less. From there, we are trying to interpret that it may be independent of the constant level. It may be still, because it is explored only on one material and with some very few data. So from this side, what my request that is there any scope to explore it in a wider way, so that idea of what we are expecting that can be accepted with some better confidence level. This was my proposition to Sundar also.
Okay. We have a question now from Manoj Yadav. The question is, are there any criteria for critical fracture energy to be termed as GFR, just like K1C or J1C?
Please repeat, sir.
Yeah, the question is, are there any criteria for the critical fracture energy to be termed as GFR, just like we have conditions for K1C and J1C? I presume he means that K1C to be a valid criterion requires certain dimensional conditions to be satisfied, and similarly for J1C.
What we tried, we observed that after 2 millimeter or 3 millimeter crack length, beyond 2 millimeter or 3 millimeter crack extension, if we measure GFR, then our proposition are quite good. But within 0 to 2 millimeter crack length, that shorter crack length, it is restricted. It is not to use the GFR. The GFR as a constant value. But there we require some GFR in terms of CTOD or other terms. But beyond 2 millimeter, 3 millimeter crack length, we can use GFR as a single material parameter to predict the ductile crack.
Okay. Any other questions from the audience? Okay. If not, please join me in thanking Professor Acharya for a very stimulating talk on a subject that most of us have probably not heard about before. Thank you, Professor Acharya. Oh, there's one more. There's a hand raised from Swapnil. Can you just type your question into the chat box? Let me see if he's able to. Okay, I'm not getting anything written there.
Sir, he is already written.
Oh, is it? It hasn't come to me yet. Oh, just a moment.
Please open the chat.
Yeah. Okay, I'm not able to. I'm not seeing anything new. I'm only seeing the first
I'll read out.
question. Yeah, could you read
So
out?
I'll read out.
Yeah, please.
Yeah. Can GFR be used in phase field fracture modeling?
Please repeat, madam.
Can GFR be used in phase field fracture modeling?
Actually, we have not experienced such kind of thing, so I cannot tell it, but it can be extended in other fields also.
Okay. Anything else? Any other questions? For some reason, I'm not getting it updated. Bharti, if you are able to see the chat box, mine is not getting updated.
No, sir, that's all. No other questions.
No other questions? Okay. Okay, then thank you again, Professor Acharya. Thank you for a very stimulating presentation. So we will send a notice regarding the seminar in July. It'll probably be around the same time with the speaker. There's one of two possibilities, and we'll let you know who the actual speaker is about the third week of July, like we have today. Okay, thank you one and all.
Thank you also from my side also. Thanks.
Thank you. Right. Bye-bye.